In this video we will derive the Maxwell's second equation for electrostatics. What this Maxwell second equation says is that the del cross E equal to 0. So when you are moving in an electric field and you are moving a charge q from in an electric field, suppose this is an electric field and you are moving a charge q in an electric field, and you are starting from A and you are coming back to the same point, then the net work done will be equal to 0. This is also known as the law of conservation of electric charge. So how to derive this is that what we have seen so far is we have seen that the electric field E can be given by the equation kq and r divided by r square. This is a direction of the field or the vector field, and then we saw that this is a unit is Newton per coulomb, and then we saw that the electric field or the electric flux density can be given as D is equal to summation by D, and D is equal to the electric flux density, and the unit was coulomb per meter square, and the total amount of flux can be given by the Gauss law, which is given by D dot ds, which is equal to the flux, which is equal to the total charge enclosed in any closed surface. And the electric flux density for a free space for a field in a free space can be given by epsilon naught E, where E is a electric field intensity. So if you say this is my first equation, this was my second equation, and this was my third equation, and based on this it was possible to derive the electric potential due to a point charge as V is equal to Q upon 4 pi epsilon naught R. So considering the case which we derived in the last case, if there is a electric field in this way which is due to a point charge located in the origin, and if you are moving a charge from a point A to a point B, this is a RA position vector and this was my RB position vector. So you are moving the charge in this direction, and if you are considering for a DL location here, which was this way, so what you can say is that if you are moving from V A to B will be equal to minus B to VBA. So the potential while you are moving from A to B, so this is due to a positive charge, and the field is also due to a positive charge. So while you are moving from A to B, you will face some form of, you are moving against the field, while when you are moving from B to A, you are moving with the field. So both these potential will be opposite, and it can be written as VAB plus VBA is equal to the line integral of E dot dl equal to 0. So what we have found out, or what we derived, is that VAB is equal to work done divided by Q is equal to minus A to B integral E dot dl. So whenever you are moving along a closed path, the summation of both these will be equal to 0, or a line integral along the total path. So suppose you moved from here to here, and then you again moved from here to here. So your total distance is, considering the 2 times which you have moved, if you are doing the line integral, it will be equal to 0. And if I am saying that this is my fourth equation, now if I am applying the Stokes law for electrostatic fields, or vector fields, if I am applying the Stokes law, which is specifically for the vector fields, if I am applying it this to this, then I can write it as E dot dl is equal to del cross E dot ds is equal to 0. So this is after application of the Stokes law, and it comes out from this equation which equates to 0, that del cross E equal to 0. So when I am moving, so this is what is known as the Maxwell's second equation. So this is what is for the electrostatic, or the conservation of the electric charge. So if you are moving along electric field, and if you are starting from a point A, if you are going to B, and if you are coming from B back to A, so that you are making a full complete circulation, or your starting point is same as your ending point, then there will be no work will be done. So this is also known as law of conservation of electric charge or electric field, and this is a Maxwell's second equation for electrostatics, can be written in this form.